Alright, we got 9.2 compound probability. A couple of vocab things here. You got a compound event. That's an event that consists of two or more events connected by the words and or. Typically, when we see the word and, we're going to take our probabilities and we're going to multiply them. And then when we see the word or, we're going to typically add the probabilities. So we'll be looking out for those key words. Sometimes with and, you might see then or and then. So if you see the word then or and then, usually that is implied an and, which means you'll multiply them. We'll see some examples in a moment. You also have a dependent event. This is the occurrence of one event that affects the other. You have independent events. The occurrence of one event does not affect the other. So we'll look at a couple of examples that'll be independent and also dependent. Mutually exclusive events are events that cannot happen at the same time. And then we'll have overlapping events. And these events are that'll have something in common. Okay, so a compound event is made up of two or more events. The outcomes of blank events do not affect one another. So this is basically just taking our vocab up there, and I'm going to abbreviate because I'm being lazy there. So independent events do not affect one another. If the outcome of an event affects the outcome of another, then we call them dependent. Basically using our vocab from up there. And then don't forget, mutually exclusive events cannot occur at the same time. Okay, so here's kind of the rules I guess I was telling you guys a little bit earlier. This one here we're going to use a little bit in the 9.5 lesson. So if A and B are dependent events, no, we will use it in this lesson. If they're dependent events here, then you're going to say, if you're trying to find the probability of A and B happening, you're going to find that the probability of A, and then you're going to multiply, and then this is the probability of B, and then this little line means given A, kind of like that, and we'll talk about what that looks like here in a second. It looks confusing. It's really not that hard, though. If they're independent events and you see the word and, you still multiply, kind of like what we got there. And then this last one here we won't use towards the end. You got the word or, and whenever you have or, typically that means you're going to add your probabilities. And that's when they're mutually exclusive, meaning that there's no overlap between the events. And then kind of the special case here, this one's a little tricky here, is if there are overlapping events, when you use the word or, you have to subtract the overlap. And we'll see that in a minute there. I'll point it out when we see it. So, first of all, we're just going to practice identifying independent versus dependent events here. So choose a number on a number tile from 12 tiles and then spin a spinner. Whatever I pick for the tile, that will not affect the spinner result. So we're going to say that these here are going to be independent events here. So the next one here, pick one card from a set of sequentially numbered cards, and then without replacing the card, pick another. So basically you pick one card out of the deck, and then you pick another card out of the deck without replacing it. This right here would be dependent events, because whatever you pick from the first time, that's going to affect, the second probability that you pick. Like, for example, if you had a deck of cards and you pulled out an ace, and then the second time you pull, well, if there's one less ace, that can affect the different probabilities of pulling something else afterwards. The next one here, roll a dice and then flip a coin. Those are totally independent there. If you, roll a 6, that's not going to affect if you land on a heads or tails for a coin right there. So that'll be independent. Okay. So when you get all that, we're going to look at a few examples here. Let's see, a desk drawer contains 5 red pens, 6 blue pens, 3 black pens, 24 paper clips, and then 16 white paper clips. I missed the first color there, 24 silver paper clips. Anyways, if you select a pen and then a paperclip from the drawer without looking. What is the probability that you select a blue pen and then sometimes they might say then or and then, but and a white paperclip. So first of all, we're going to find the probability, first of all, selecting a blue pen right there. So this kind of uses a 9.1 lesson here. There are, let's see, blue pens. There are 6 of them. And we also need the total. So let's go find that total there. The total, we're just going to add up all the pens there. So you got, what do we have? 5 red, 6 blue, 3 black, and I think that's it there. So there should be, what, 14 total. And then the 6 blue pens out of the 14 right there, that should give you the probability of A. We can reduce it if we want. We could call that, let's see, they're both divisible by 2, so that'd be 3 over 7. Or you can go and get the decimal there for that. 3 over 7 is roughly 40 or 0.42, let's call that 429. Okay, so now we'll need to go find the probability of selecting a white paperclip. So this is a different total. Now, so the paperclips, you had 24 total, or you had 24 of one and then 16 of the other, so that should be 40 total. So for the probability of B here, we're just going to do, B is selecting the white. There were 16 white, so we'll go 16 and then out of the 40. And I think those are both divisible by 8. That would be 2 and then 5 right there. Okay, so then when you're going and finding the probability of A and B happening at the same time, you're going to do 3 over 7, the first probability, and then times the probability of getting the white paperclip, 2 out of 5. And then you can either use your calculator. That one's not too hard to do. That's just 6 in the numerator and then 35 in the denominator. You can leave your answer like that, or you can go get the decimal. 6 out of 35 here. That's about 17.14%. You could write it like 0.17 like that, or you can say that's roughly 17%, kind of like that right there. I usually write it as a percentage, but just be ready for either fraction, decimal, or percent form. So yeah, that's how you do that. So these here are independent events. If you pick, a blue pen, that's not going to affect the paperclip. So therefore the probability, okay, about 17%. We already kind of did that there. Okay, now this next example here, I like this one here because out of the same desk drawer was a probability of you choosing a red pen and then a blue pen without replacement. So this time you're picking from the same category and you're not going to replace. So these are going to be dependent events here. One, whatever happens in the first event is going to affect the second one. And it kind of sounds confusing. It's actually not going to be as hard as you think it is here. So there were, let's see, 5 red pens. So let's go 5 out of, what was it, 14? Yep, 5 out of 14. And that's the probability of choosing a red right there. I'll just call it probability of red right there. 5 out of 14. And then probability of blue, but then given that you've already picked the red right there. So I'm going to kind of write it like that right there. You don't really need to know that notation that much. You just really need to think logically. Okay, if I pull out one pen, now I only got 13 to pick from. So instead of out of 14, we're going to have out of 13. And then what are we doing? A blue pen. If we picked a red the first time, then all the blues should still remain. There were 6 blues. So then we'll go 6 out of 13 right there. And then is like an and, so and then, so that's going to be multiplication. So we'll go 5 over 14 and then times 6 over 13 like that. And that's all you got to do there. You could reduce a little bit. I'm just going to multiply across here. This would be 30. 14 times 13 is 182. 30 out of 182. It's about 16.5% right there. You could reduce a fraction if you want. I believe both of those are divisible by 2 at least, maybe even more. Let me see. Oh yeah, it would reduce to 15 over 91 if you wanted the reduced form right there. So yeah, each of them are just slightly different here. This is kind of more notational. Really the thing you need to think about here are the fractions. So there were 5 of those red pens out of 14, and then after we picked, there were still 6 blue pens, but then only 13 pens to choose from. All right, next one here. Using the same desk drawer was the probability of choosing a red pen and then a silver paperclip. So we're going back to an independent event right here. Picking the red pen is not going to affect the paperclip. But then it's then, which is an implied and, so you're going to multiply again. So let's see here. There was red pen again, so there's 5 of those out of the 14. And then you're going to multiply silver paperclip. Let's see, I think there's 24 out of 40 there. Whoops, 24 out of 40, not 20 there. All right, and then, yeah, I'm just going to multiply cross. Once again, you could cross reduce and do all that stuff if you want, but let's just go ahead and get it here. That's 120, and then 14 times 40 is 560. It comes out to about 21%. If you want the reduced fraction, it'll come out to 3 out of 14, believe it or not. But then that'll be about 21.4% chance of happening. So you just multiply them. If you want to go and get, all the notational stuff, probability of picking a red was 5 out of 14. Probability of, silver, given that you got the red right there, which really, it doesn't really change anything. That was the 24 out of 40. So anyways, there. Key thing, multiply. And then pay attention if you need to decrease the numbers by 1 or 2 or anything like that. So, okay, now in this next one here, we have some tiles, and we're going to choose here. Find the probability that you choose a dotted tile and then a dragon tile. Key thing is you replace. You're going to replace the first tile right there. So this is going to be an independent event. Whatever I pick from the first thing, since I'm replacing it back in, and then going to pick again from 15, these are independent of one another. So I guess there's 15 tiles total, and let's go find the probability that we pick a dotted tile. There's 4 of those, so we'll go 4 out of 15. And then let's see here, we have dragon tiles. Looks like these are dragon guys here. Looks like there's only 3 of those, so that'd be 3 out of 15. And then since we are figuring out, they said then, and that's implied and then, so that's a multiplication. We'll multiply the 2 probabilities here. So we'll go 4 out of 15, and then times 3 out of 15. That should be 12 out of 225. That should reduce a little bit. 12 out of 225. That comes out to 4 out of 75 if you want the reduced fraction. The percent is going to be 0.053. So what is that? This is 5%, 5.3%. And then that will be it right there. And that is if you are replacing. I like 4 and 5 here because 5 is pretty much asking the same exact thing, except we're not going to replace. Without replacing the first tile, you select a second tile. What's the probability that you choose a dotted tile and then the dragon tile? So we'll see how this affects the probability. The probability of dotted should be the same if we're doing that one first right there. So that's going to be 4 out of 15. The probability of the dragon, but then given that we did the dotted first and we're not replacing, now we got to think about, okay, how many tiles would I have left if I pulled that first tile out right there? So if you pulled the first tile out and there's not one, if there's one missing, there should be only 14 tiles to choose from. And then you were doing the 3 dragons out of 14. So it'll change things just a little bit. It's not going to be drastically different, but it will be a little bit different. This should be 12 over, let's see, multiply that 210. And then 12 divided by 210. The fraction is, what is this, 2 out of 35. And then for the percent, it's about 0.05. And then 7, so it's about 5.7% if you move the decimal over twice. So just a little bit more likely to happen, but not much more right there. Okay, so that is that right there. Let's look at this one here. You roll a standard die and then spin the spinner on the right. What is the probability that you roll a number less than 3 on the spinner, and then and the spinner lands on the vowel? So another and going to multiply. So this one we just got to think about. We're not given tiles or anything. So probability that you roll a number less than 3. We want to think of how many numbers there are less than 3 on a typical dice. So 6-sided dice, you got 1 through 6. Numbers less than 3, so that would be 2 and 1, and there's 2 of those, so it'd be 2 out of 6 for that first probability. And then what are we doing? A vowel on this one here. A vowel, the only vowel I see is U right there, so that's 1 out of 4 right there. And then once again we'll multiply. That'll be 2 out of, what is that, 24. 1 out of 12, I can reduce that pretty easy. 1 out of 12 as a decimal is 0.08 or 8.3% right there, and that 3 I guess repeats right there. So that is that probability. Those are dependent of one another. One will not affect the other at all. Okay, so that's that. All right, number 7, athletes at a local high school may participate in one sport each season. Was a probability that a randomly selected student athlete plays volleyball or is a swim team. If we see that keyword or, typically we will add the probabilities here. So the probability of selecting someone that's in volleyball, let's look at the color codes. Volleyball, I guess that's a darker green, that's going to be 10%. So they're giving us these as percentages here. Probability of swimming, looks like this darker blue, I believe it is at 24%. So we'll just add those, and or just says take those percentages and literally add them together. So it's about 34%. So the or ones are kind of easy there when you're doing those. Okay, what is the probability? You choose a card from a deck of cards. What is the probability of choosing a queen or a king? So if you're not familiar with the deck of cards, 52 total. Usually there's going to be 4 kings for the different suits and then 4 queens. So what's the probability of choosing a queen or a king? So since there are 4 queens, we would say that's 4 out of 52. Okay, and then they do use the word or, so we do need to add. And then there are going to be 4 kings, so that's 4 out of 52 there. So total of 8 out of 52. And 8 out of 52, I think it reduces a little bit. I think at least both divisible by 2. Oh, okay, both divisible by 4 right there. That'd be 2 out of 13. 2 out of 13, probably not a very pretty decimal. 0.1538. Yeah, let's call that about 15.4 after you round. 15.4%. And that'll be it there. Okay. What is the probability of rolling either a 5 or a 6 on a standard die? So there's only 1 5 and there's only 1 6, and we're doing the keyword or, so it's just 1 out of 6 total and then 1 out of 6 total. You're not actually going to use the numbers 5 and 6. You're thinking about how many sides are 5 or how many sides are 6 on a standard die. So add those up. That's 2 out of 6. Remember, add the numerators. Denominator stays the same. Reduces to 1/3. That's about 33.3 repeating percent chance. Okay. Probability of selecting a letter out of the alphabet and getting either an A or a C. there should be only one A out of the 26 letters, and then there should only be a one C out of the 26, so that would be 2 out of 26, 1 out of 13, which comes out to about 7%, 7.7 once you round. And that'll be it. Okay, so those are traditionally not too hard for you guys. These will kind of mess you up here is when you have overlapping events. So think about this here. The probability of rolling either an even number or a multiple of 3 when rolling a standard die. So most of y'all would say, oh, okay, I see the word or here, and then the probability of rolling an even number on a die, there's 3 of those. You got 2, 4, and 6. So y'all would say, okay, 3 out of 6. And then a multiple of 3, so something divisible by 3, there's only 2 of those numbers out of the 6 total. And then if you think, there's actually some numbers that are an even and a multiple of 3. And actually, if you think about that, there's only one of those. And that's our overlapping event. And the deal is, when you're adding the probabilities up, you're kind of already adding those together. It's already accounted for in the probability. So the big idea with the probability formula is we subtract, we've already written this, but we subtract the overlap. And in this case here, the overlap is the ones that are multiples of 3 and at the same time an even number. And that the only number that would satisfy that would be the 6 right there. 6 is even. 6 is also a multiple of 3. So there's 1 out of these 6 sides there. So we're going to go and do 3 out of 6 plus 2 out of 6, and then we're actually going to subtract the 1 out of 6 right there. And that comes out to 4 out of 6 total. That's about 2/3 or 67% once you round. So the big thing is subtracting the overlap. When I took probability in college, I would always get tripped up on these here because I wouldn't pay attention for the overlapping ideas there. So just kind of be careful there on that and look out for those there. Still dealing with the dice here. What's the probability of rolling either an odd number or a number less than 4 when rolling a standard die? So an odd number, there would be 3 out of 6 of those. Numbers less than 4, there's actually going to be 3 out of 6 of those. So if you just did your traditional adding, you'd say, oh, that's a 100% chance, but it's not quite a 100% chance. There's overlap, and since there's overlap, we need to subtract that. The overlap here, in this case, we need to think of odd numbers that are also less than 4. They're going to be 2 out of those numbers there. I think 1 and 3 would both be less than 4 and odd. So we'll go, this one will look like this here, 3/6 plus 3/6, but then subtract 2 out of 6 because of that overlap. You're basically already adding a couple of overlap probabilities, so we got to take it away to keep it all balanced out. That comes out to 4 out of 6, which is 2/3. Again, that was kind of a coincidence that came out the same, but about 67% there once you're done. All right, for this last one here, what is the probability of selecting a random letter out of the alphabet and getting consonant or one of the first 5 letters of the alphabet? This is another one here where we do have a little bit of overlap here. So consonant, there's 5 vowels, I believe, right? A, E, I, O, U. Those are your 5 vowels. So that means out of the 26, there should be 21 consonants out of the 26 total. You got the keyword or, so we need to add. There are 5 of the first 5 letters of the alphabet, but then there are some overlapping letters there. So let's think about the overlap. So the first 5 letters, A, B, C, D, and E, of those, there are 1, 2, 3 consonants. So we'll go 3 out of 26 right there. So I need to go back and subtract that. All right, so I think that comes out to 23 out of 26 right there. And let me type that into the calculator. That does not reduce any further. So that's about 88.4%. Actually 0.5 after you round up. And that'll be that one there. So make sure you subtract that overlap on that one.